If we have a reaction that is at equilibrium and we do something to disturb the equilibrium, Le Chatelier's principle helps us to decide what effect that disturbance is going to have. So if we add reactants, what is going to happen? If we take reactants away, what is going to happen to our chemical equilibrium? And it's going to shift towards the direction to minimize the disturbance and again return to equilibrium, where the concentrations of all the chemicals have changed, but our equilibrium is restored, and that our equilibrium constant remains the same. Let's look at some individual cases. So what happens when we add reactants into our chemical reaction? This is going to increase the concentration of the reactants, which is going to increase the rate of our forward reaction. Because it doesn't have any effect on the rate of the reverse reaction, our reaction is going to move to the right towards the products. And at the new equilibrium position, the reactants and the products will be at a value that keeps our equilibrium constant the same, but under that initial addition, our reaction is going to shift towards the products. What if we remove reactants? If we're removing reactants, that's decreasing their concentration. It decreases the rate of the forward reaction. So the products are going to form more reactants, and the reaction is going to proceed to the left towards the reactants until our equilibrium is restored. The new equilibrium position, those concentrations of reactants and products will have adjusted so that the value of that equilibrium constant remains the same. Let's look at the case where we're adding product. If we add NO2 into our chemical reaction, that is going to make our Q value larger in the numerator, shifting our reaction towards the left. It's going to shift towards making more of the reactants. And so our chemical equilibrium upon adding products shifts towards the reactants to reestablish the equilibrium. If we have a reaction in the gas phase and we add gaseous reactants, this is going to increase the partial pressure of the reactants, causing our equilibrium to shift towards the products. It does increase the concentration, but it does not increase the partial pressures of the other gases, just the partial pressure of that particular reactant. Another case that we could have is if we're adding inert gas to the mixture, so something that's not participating in our chemical reaction. This has no effect on the position of equilibrium because it doesn't affect the partial pressures of any of the other gases in the reaction. What if we change the volume? So if we have gaseous reactions and we decrease the volume of the container, by shrinking that volume, that increases the concentration of all the gases that are present, increases their partial pressures, but it does not change the concentration of solutions, only gases. Okay? If their partial pressures increase, the total pressure in the container will also increase. So what this means is it doesn't give us an exact direction that the equilibrium is going to shift, but we're going to try and shift it to remove the pressure that is present. So we are actually going to shift the reaction towards the side that has fewer gas molecules, which would decrease the pressure. So if we decrease the volume, we're going to shift to the side with fewer gas molecules. If we increase the volume, then we'd shift towards the side with more gas molecules. Okay. So as we increase pressure, we're going to shift towards the side with fewer gas molecules. So in this case, we're looking at nitrogen and hydrogen. We've got 4 moles of gas on the reactant side. We have 2 moles of gas on the product side. To decrease the amount of pressure inside that container, the equilibrium is going to shift towards the side with less molecules. If we decrease the pressure, then there's more room in the container, and we're actually going to shift towards the side that has more gas molecules. The effect of temperature on a chemical reaction depends on the type of chemical reaction that it is. It depends if it's an exothermic reaction or an endothermic reaction. If we have an exothermic reaction, remember it's giving off heat, which means that heat is a product in our chemical reaction. So increasing the temperature is similar to adding heat. So if we look at Le Chatelier's, if we're adding a product, we're going to shift away from that heat. So if we're adding heat, our reaction is going to shift towards the reactants. If we remove heat, either by cooling the reaction, that means that we're removing heat, we're removing some product, and we're going to shift the reaction towards the product side. For an endothermic reaction, now we can think of endothermic reaction as having heat on the reactant side of the chemical reaction. So this is, if we're increasing the temperature, it's like adding heat, like adding a reactant. And so according to Le Chatelier's principle, we're going to shift away from that added heat, which means we're going to shift towards the product side. So our reaction is going to shift right. We're going to have a larger equilibrium constant. If we look at a particular chemical reaction, we can see this effect by a color change. So you have dinitrogen tetroxide. It's a colorless gas. It's an endothermic reaction. And we have nitrogen dioxide, which is a brown gas. By looking at the color change, we can see the equilibrium shift occur. If we lower the temperature, that's similar to removing reactants, and the equilibrium is going to shift towards the reactants. So at a lower temperature, when we're cold, that equilibrium is going to shift towards the colorless NO2 gas. N2O4 gas. If we raise the temperature to a higher temperature, we're going to shift. It's like adding reactant, and so it's going to shift the equilibrium to the right, to the higher, or to the visible brown gas of nitrogen dioxide. And just in case you were curious, so nitrogen dioxide, this is one component that does make up smog. So that's kind of what leads to that hazy color in the sky that you associate with pollution. How about a catalyst? How does a catalyst affect our equilibrium? Well, it does provide us a different mechanism, more efficient mechanism, and so it works both for the forward and reverse reaction, however. So adding a catalyst has no effect on the position of our equilibrium. Let's practice. See if you can determine the direction that the reaction will shift for sulfur dioxide plus oxygen, giving us sulfur trioxide. There are multiple scenarios to determine which direction the reaction will progress. Pause the video to determine your answers. Let's look at adding more oxygen. So adding more oxygen into the chemical reaction is adding reactants. which is going to shift the equilibrium towards the product. So we'll shift to the SO3 towards the products in the chemical reaction. What about if we condense the SO3 to remove it from the chemical reaction? So if we condense the SO3, we're essentially taking it out of that chemical reaction, removing it, which decreases its concentration and means that our reaction is going to shift toward the products to maintain our equilibrium. So it's going to shift to the SO3 in this case. What if we compress the gases? So if we compress the gases, we're increasing the pressure. We're going to have to look at the coefficients in front of our balanced chemical reaction. By compressing the gases, we have more moles of gas on the left side of our reaction and less on the right. So this is going to shift towards the side with less moles of gas. So we're shifting to the SO3. What if we cool the container? Well, cooling the container, we're going to have to look at the enthalpy. So the enthalpy in this case is negative, which means it's an exothermic reaction. The heat is on the product side. By cooling it, we're essentially removing heat from the products, removing a product, which allows our equilibrium to shift toward the product side, which is SO3. If we double the volume of the container, we're increasing the size, decreasing the concentration, which means that we're going to look at the coefficients. We'll have more room, and so we're going to shift toward the reactants in this case. So we're going to shift to the SO2 toward the reactant side of the container. What if we warm our container mixture? Again, we're looking at our enthalpy. We're thinking about heat as a product. And so by warming it up, we're essentially adding product in, which means we're going to shift to the reactant side, the SO2. If we're adding an inert gas is going to increase the pressure of the overall container, but not the partial pressures of each of the gases, and so this will have no effect. Adding a catalyst to the mixture, again, gives us an alternate pathway, but has no effect on the overall equilibrium.